Good morning. So, this morning you should have picked up an example sheet as well as a handout. Just a little word about the example sheets. It is essential that you do these examples. If you try and go into the exam in January without having done these examples, you'll be lost. So please have a go at them. The example sheets are here on the website if you lose a piece of paper. Furthermore, if you can't do them, the answers are there as well. These are not assessed, and they're here to help you learn. So if you have problems, if you really don't understand, please get in touch, see if I can help you. But that's an example sheet then on these first 4 lectures that I've been teaching you last week and this week. Okay, so please make every effort to do them. Traditionally, students tend to do these the day before the exam, and although it's better to do it the day before the exam than not to do it at all, it does leave you somewhat short of a margin for error if you can't do them. So, just a little note there. Okay, so as usual, we start off looking at the weather. I'm going to start off with something slightly different. This is just to draw your attention really to the Whitworth Meteorological Observatory, which is an observatory that our school runs, and it's on top of the George Kenyon building, which is on the campus here. So essentially, it's the weather here in Manchester. So over the past 24 hours, so this is 24 hours of data from yesterday morning to this morning, and this is pressure. You can see the pressure is falling, and fell to a minimum at about 4 o'clock this morning, rising slowly. Of more interest, perhaps, is the temperature. Now, I don't know whether you were sufficiently awake this morning and realised, blimey, it's warm. Walked out the flat this morning and thought, what's happened? And somewhere, well, we can see what's happened. This is yesterday morning. The more reliable temperatures are the coloured ones, actually, on this. There are 3 different thermometers. These 2 work best. So, it's 7.5 degrees yesterday. 14 degrees today, 7 degrees warmer. And what's happened? Well, it obviously warmed up during the day yesterday. It didn't get very cold overnight because it was very cloudy. And then something happened here between about 10 o'clock and about 4 o'clock this morning. So the temperature really shot up. So it went from 8 degrees to 14 degrees. That's quite warm. That's 6 degrees, basically. So, what else happened? Well, here's the relative humidity. Well, at the same time, the relative humidity was 100%. So, it suggests that it was raining, possibly, quite possibly. If you were out and about last night, you'll know the answer to that. Maximum in dew point temperature. So, again, there was this big peak in dew point temperature, also 14 degrees, because the relative humidity is 100%. And wind, yeah, well, it's much more windy than yesterday. Yesterday morning, hardly any wind, a couple of meters a second at most, and then today we've got 6 degrees. So the black lines on here are the average, 10-minute average winds, and then the red are the gusts. So that's I think it's a 3-second gust with this machine. Gust there isn't a particularly good definition of gust. It depends which. Each instrument has its own algorithm, it seems. But anyway, gusting up to about 14 meters a second. Quite a stiff breeze in places. And here is the rainfall. So between 10 o'clock and 4 o'clock in the morning, it was raining quite significantly. We had 4 millimeters of rain overnight. 4 millimeters of rain isn't going to cause flooding or anything, but it's, you notice it. So if you were trying to find your way home last night, you would have been aware of this. Okay, so what we've got, warm temperature goes up, it rains, the wind picks up, and the wind direction changes a little bit. So during the same sort of period, the wind direction was, so the southwesterly, this is about 220, and it went to westerly. So there is a shift in the wind towards, from southwest to west towards the north. And they are all hallmarks of the passage of a front, right? Passage of a front, change in temperature, rainfall, shift in the wind, change in the wind speed. They're all suggestions that there might have been a front. Well, the story wouldn't be complete without showing you some fronts. That's the weather chart for midnight when it was raining, and you can see slap bang on in the middle of it. The UK is in the middle of these fronts. Now actually the active fronts in this case are these warm fronts, so there's actually two fronts on there. Probably the Met Office overdoes fronts, so this was probably the main front at that time. Although the fact that it rained overnight suggests that's why they've put two fronts in here. Doesn't matter whether there were one or two fronts, the fact is that there were fronts there, and that's why we got the rainfall. And we can see there's a cold front behind here. So front, yes, we had a warm front. Warm front means warm air displacing cold air, and so yes, it's consistent with the temperature going up. So warm front means the temperature goes up, and the shift in the wind is well, you can see the shift in the wind. You can't immediately from here, but it does. Here the wind is sort of southwesterly. The isobars are pointing towards the northeast, and then here they're more westerly, which is consistent with what we saw. If we look at the rainfall now, so this is the Met Office radar now, so there's 9 hours later than that chart, there's nothing to see. A few spots here and there, some showers in the northwest, around Scotland, patches of rain here. Nothing much. So what's happened to all those fronts? Well, basically they move quickly. This is a picture from the satellite site, and it has an algorithm that produces rain. So you can see the rain, and you can see it moving. This is animated. You can see it moving towards Scandinavia, and that's the rain that was passed over us overnight. So you can see it's basically crossed the North Sea in the period. So that's the front, that's the North Sea. The infrared picture shows, so if we look at the infrared picture, we can see here sort of high cloud over the UK. This is current, this is, well, that's 8:10 BST. And we can see this kind of cold front stretching up into the west. But of more perhaps eye-catching is down here, south of us, in the Mediterranean region. There's these very bright clouds here. These are thunderstorms. This is deep convection. We can tell they're deep convection because they're kind of globular. These things are globular clouds. And if we look at the weather chart again, this is for midnight, but we can see that there's a depression in the Mediterranean. There's actually been a lot of concern in the Mediterranean by people who live in the Mediterranean that there was going to be a medicane. A medicane is their version of a hurricane. They don't really have hurricanes in the Mediterranean, but they have occasionally these very, very strong windstorms. I don't think it's developed into a full-on medicane, but it's obviously produced some pretty hefty thunderstorms down in that part of the world. If we look at the upper air chart, so I'm trying to relate things between the surface and the upper air. This is for 6 o'clock actually. It'd be easier if I'm trying to relate it to the surface to bring it back to midnight. So this is midnight. So this is when these fronts were over us. You see this on here. So this is showing a warm front in the North Sea, cold front coming down over Scotland. So if we look at this plot here, here's a gradient in temperature of, and that's in the North Sea. So the gradient in temperature is consistent with the warm front. So this is the gradient in temperature going from the yellow colour to this sort of greenish colour here. That's the gradient in temperature of the warm front, and this similarly gradient in temperature of the cold front. The surface cold and warm fronts are positioned. The cold front is at the front edge of this gradient. The surface warm front is at the rear edge of this gradient. Okay, so they're not in the middle of the gradient, they're at the front edge of the gradient where you position the surface fronts. That's a bit of an aside, I suppose. But what you're seeing as we come down here, you can see in this region around where the Mediterranean is, this is the low pressure system. At midnight, obviously it's moving, so that's why the showers are moved further south now. So it's part of this extended trough system that we can see over. So this is a ridge over us, and there's a trough there in the 500 millibar flow. And these black lines, okay, so the black lines are showing a trough and a ridge pattern. And in fact, this is about to cut off into a separate feature. So if I run it forward, there you can see it. And that's called a cut-off low, actually, this feature here. And it tends to have a bit of a life of its own and hang around for quite a while. So they'll have that feature there for a long time. Generally speaking, the main jet stream, so this is the main jet stream, it follows this path like this. It's quite mobile, so these sort of troughs and ridges, as you look at this, I'll flick through it and you can see how the features in the pattern move from left to right. It's pretty obvious. See how the pattern's moving from left to right? But this thing has stayed in the same place. And now there's another feature here which is about to do the same sort of thing. So there it's going, there it's cut off like that. These are called, so the undulations that are moving from left to right, these things here are called Rossby waves. And Rossby waves break, that's what a breaking Rossby wave looks like. Well, I'm going to have a lot more to say about breaking Rossby waves later on in the course, but it's a nice example on this particular day. And I have to take my examples when I get them, if I'm trying to use the weather on the day to tell you what's happening, because sometimes the weather doesn't play ball with what I wanted to do. So on this day then, we've got, oops, I need the other one, don't I? This one. We've got all these showers down here. And we're going to be talking about tephigrams today. That's going to be the main point of the lecture. And I'm just going to show you a tephigram from Sicily. So this is at midnight from Sicily. Trapani is in Sicily. Now what you see, so this is a slightly different thermodynamic diagram, but it looks very similar. What you have is temperature, humidity, and you have this layer here, which is actually quite unstable in the lower part of the atmosphere. So we'll come back to that and explain a bit more when I've had a go at explaining stability on the tephigram. So that's something to describe to you. And then I'm just going to contrast this. This is Valentia in southwest Ireland, and you've got very much a different, so this is sloping completely the other way. So different stability characteristics, and if we look at there's no convection around southwest Ireland. Okay, so that's all that. That's showing you basically what fronts look like, how we experience them on the ground, looking at the surface observations, and a little bit about how Rossby waves work. Yeah. So these are all going to be themes we shall develop theoretically in the course. Any questions? Everybody happy? Well, everybody's awake, apparently. Not such a bad thing this time of the day. Okay, so to tephigrams then. So just to remind ourselves where we got to yesterday. Okay, so I finished off with this yesterday. So this is a picture, this is a tephigram, and it has a lot of lines on it. Remember, there are 5 different kinds of line on these plots. There's the lines that slope up and to the right, the straight lines going up and to the right. These are isotherms. lines of constant temperature. Sloping up and to the left are lines of potential temperature. So the basic graph of the tephigram is temperature, entropy or potential temperature, and it's rotating through 45 degrees. These lines, which are quasi-horizontal, are lines of constant pressure, and they're labelled on the right-hand side there. It's basically going up to 300 millibars. And then there are two other sets of lines, and they are lines relating to water vapor. So there are quite faint lines, constant mixing ratio lines here. So these are the lines that are pointing, they're sloping up and to the right as well, but they are sort of dotted lines, lines of constant mixing ratio, and they're labelled here in grams per kilogram. And the fifth type of line, which are these sort of broad dashes, which are sort of gently curving upwards, these are the saturated adiabatic lines. It's all that information on the tephigram. And what do we do with a tephigram? Well, we plot radius-on profiles on a tephigram. So here's an example. Temperature and dew point are the things that we plot. So temperature of 7 degrees at 1,000 millibars, for example. This is 1,000 millibars. So where's 7 degrees? Well, this is temperature of 0, temperature of 10. 7 degrees would be around here. So there. At that point, dew point is 6, so we point the dew points a little bit to the left. At 920, they have the same, and so the 2 points are plotted together. Now that's a saturated layer. The temperature and dew point are equal, and then after that, they diverge, and we keep on plotting. So to plot on the tephigram, you say, okay, there's the pressure, find the temperature, dew point. Try the dots up. Usually with tephigrams that you get, by the way, the joining dots is the dots, as you can see, are somewhat randomly spaced, and they're randomly spaced because originally somebody would have got a much more high resolution tephigram, and they've chosen these points so that you can draw lines between them and reproduce what was there. So that's one example. So basically you take the temperature profile and plot it on here. You take the dew point profile and plot it on here as a temperature. So you have two curves. And here's another example. We'll do the same sort of thing. On this one we have an inversion layer at the surface, very similar to what was there in Valencia this morning. So we can see a bit of a cloud layer, inversion layer there. The secondary tropopause at the top of the diagram. Here's another example plotting another profile, and in this case there's another, I've plotted this as a frontal inversion layer. If you get these inversion layers in the mid-troposphere, they're nearly always caused by fronts of some kind. So that's what I've plotted there. Obviously it doesn't tell you what kind of front it is, it just says it's a front. Okay, so if you find yourself doing the examples and a bit bewildered about how to plot tephigrams, then try and look at these simple examples on here. That will get you going on that. There is no other way other than to do it yourself to learn this. You're not going to learn it just from listening to me. Yeah, you are going to have to get hold of these. You can plot the tephigrams. You can get them off the web page, plot them, and have a go. Because otherwise it's not going to work. Okay, so that's just basically what we've got, what they are. But it doesn't make a great deal of sense until we see how to use them. And so that's what I'm going to go talk about now. How do we actually make use of the tephigram? And from that, I hope you'll understand a bit better and see why. Because until you see something in action, it's difficult to understand what it's about. Yeah? So, well, like I said last time, there are two things you can do with a tephigram. One is you can basically just convert different units of water vapor. It's a sort of graphical way of converting different things. And here I'm converting dew point to mixing ratio. Now dew point, okay, I'm given dew point and I can plot it on the tephigram. So here we are. What's the mixing ratio of a parcel of air which is a dew point of 10 degrees at 800 millibars? And we can see here, here's 800 millibars, so we follow this along, and 10 degrees is this sloping line here, so where they intersect we plot that, and that's our dew point. Okay, we've plotted the dew point, and so to find the mixing ratio, we just read that off these dotted lines here. So there's 7, here's 10, and so obviously it lies somewhere between 7 and 10. In this case it's pretty close, so I've estimated 9.8. Now you're not going to get 4 significant figures out of this kind of approach. Obviously it's fairly approximate. It's as good as your eye can read of these diagrams. But often you're not looking for very high precision in this game. One of the challenges of measuring things in the environment, measuring things like water vapor and temperature, is the fact that they are not constant over large distances. You have representativity errors, as they're called. In other words, the dew point measured here might be rather different to the dew point measured in the city centre, for example. Or down in Fallowfield. They would. So looking for high precision in these measurements is often spurious. The error in the measurement is overwhelmed by the actual environmental error, if you like, the noise in the actual property being measured. So that's how you do dew point to mixing ratio. That's a nice simple example. Here's a little less simple dew point to relative humidity. Okay, well, relative humidity is it's the ratio of the vapor pressure to the saturated vapor pressure. So it involves both temperature, saturated vapor pressure. It's a function of temperature. It involves both temperature and the dew point. So we need both lines. So we need to know temperature, 15 degrees in this case, and a dew point of 10. Again at 800 millibars. And so I'm plotting both of these here. So these are two points, dew point and temperature. This is 15 degrees, halfway between 10 and 20 along the 800 line. And I'm using a slightly different definition of relative humidity here. The one I gave before was the ratio of the vapor pressure to the saturated vapor pressure. But because the mixing ratios are proportional to the vapor pressure at constant, provided you keep the atmospheric pressure the same, and in this case they are both at the same atmospheric pressure, then we can just use the mixing ratio divided by the saturated mixing ratio. Okay, so mixing ratio we can get like the same one as before. So the mixing ratio, you just read down to here, there's parts and millibars. We got the scale at the bottom actually, so it's 9.8 gram per kilogram. That's what we got before. And the saturated mixing ratio, well, we just take the mixing ratio line through the temperature. So this is the temperature, and if the air was saturated, it would also be the dew point. So that would be the dew point if the air was saturated. And so if the air was saturated, that would be the mixing ratio. Turns out to be 13.6, reading between these 2 points here. And so we get a relative humidity ratio between the two of 72%. Again, if you did it, you'd get a slightly different number, but again, it gives you a good estimate of the relative humidity. So it's an easy, quick way of getting the relative humidity. You can obviously do it numerically, and there are almost certainly many websites that will do it for you numerically, but that's how you do it graphically. So in a sense, you could easily write a computer program to do that. That wouldn't be too difficult. But the other use of a tephigram, it would not be easy to write a computer program to do, because we have to take into account the whole profile. And that's looking at this idea of the stability to convection of the profile. Remember, we've looked in a previous lecture on the parcel approximation. So we take a parcel of air and we lift it, and in this hypothetical experiment, we don't allow it to mix and we don't add or remove heat. The adding or removing heat is a pretty good approximation. The not mixing isn't a good approximation, right? The real convection in the atmosphere is a turbulent process and necessarily involves mixing. So this is a bit of an idealization. However, it allows us to make some progress with this problem, which otherwise is intractable. Turbulence is not an easy problem to take on. So here's my diagram again. So I've shown this diagram in a previous lecture, temperature and height along the y-axis. Parcel, this is the temperature of the parcel as it's lifted. It falls with the dry adiabatic lapse rate until it reaches saturation. And that point is called the lifting condensation level. The height that a parcel of air must be lifted to reach saturation. You usually find this in the boundary layer, and that will be your cloud base. So you'll be familiar with usually when you look at this, there's some sort of cloud base, some sort of level of the cloud above you, which is reasonably consistent as you look around the sky, and that would be because it's governed by this process here. So that's the lifting condensation level. If we look at this process on a tephigram, we have this construction. So there's one slide from this lecture that you should remember. It is this one, right? Make sure you understand this one. So, what I'm doing is the same thing as on the previous slide. I'm taking a parcel of air and lifting it, and I'm following its path on this tephigram. This is part of the tephigram, blown up to make it relatively easy. So, we start off with a temperature. So the temperature's here. It's 25 degrees in this example. And this is the dew point, which was 8.5 in this example. So it was a hot, dry day, in fact, on this case. Okay, so as you lift the parcel of air, okay, so the parcel of air has two properties, temperature and dew point. And as you lift it, both of them change, right? One of them changes according to the dry adiabatic lapse rate. We know that. There's the dry adiabatic lapse rate. It is the line of constant potential temperature along here. What happens to the dew point? Well, the dew point changes with height. Okay, well, it's pretty obvious, this red line, this would be constant temperature, and clearly it doesn't have constant temperature. But it does have constant mixing ratio. Because if we're assuming that the parcel doesn't mix with its surroundings, the ratio of water vapor molecules to air molecules doesn't change. It can't change. Nothing to change it. So it stays the same. And so you follow this. This is a mixing ratio line here. You follow that line, and then, of course, as you come up through the atmosphere, the parcel gets colder and colder and colder. So 900 millibars, its temperature has fallen to, this is 20, this is 10, and that's about, I don't know, 16, something like that. As it comes up to 800 millibars, its temperature is, well, here we've got about, I don't know, 7 or something like that, 6 or 7, between 10 and 0. And then, bang, they hit each other, they meet. And where they meet, things change. Cloud forms. There's the lifting condensation level. In this case, it's 780 millibars. Around, I don't know, around a kilometre somewhere in the atmosphere. So then, as we continue to lift the parcel, it follows the saturated adiabatic line, which is this line here. So it basically follows a path between these two. So that's what this blue line here is. It's basically following these two lines here. So you can see all of the different elements of the tephigram coming together in this construction, this three-legged construction. The rest of the lecture is going to be applying this three-legged construction. Any questions on the three-legged construction? Like I said, this is the take-home message. I'll make sure you understand. Any questions? Any shock or horror? No horror even. Okay. Just to make a point, by the way, why did the parcel lift from the surface? Well, something as simple as a flow over a hill forced it to leave the surface. So we're talking about a parcel of air that for some reason has been mechanically lifted from the surface. The other thing that can lift a parcel of air is a front. Okay, so either lifted by a front or lifted by flow over topography. Those are the things. Not free convection. We're not talking here about free convection. This is mechanically lifting a parcel. We haven't reached free convection yet. Okay, so those are the three elements. The dry adiabatic, the temperature falling along the dry adiabatic, the dew point falling along the mixing ratio line where they meet, they both then follow the saturated adiabatic line. And that's all calculated on the tephigram. Okay. Unfortunately, some enterprising chaps decided this was merited the description of a theorem. It doesn't, by the way. It is not a theorem, but that's what it seems to be called in the literature. This is the same construction as before, but what I've done is to project this line, this blue line, back to the surface. And when we get to the surface, what have we done? Well, this parcel of air is saturated all the way down, because that's the saturated adiabatic. So as it comes down, it's obviously increasing its pressure, it's trying to warm up. So in order for it to keep saturating, you've got to keep evaporating air into it, evaporated water, sorry, into it. The energy for that is coming from the air, so it doesn't warm up along this line. It has to warm up rather more slowly. And that basically is the definition of the wet bulb temperature. So the temperature you get to here is the wet bulb temperature. It's the temperature you get to if you cool a parcel, evaporating it into it to saturation. And that's basically what we've done here. So the mixing ratio line through the dew point, the temperature, the dry adiabatic to the temperature, and the saturated adiabatic to the wet bulb temperature meet at this point at the lifting condensation level. Sometimes these lines here, these saturated adiabatics, are called constant wet bulb potential temperature lines and labelled as such. So that's the only reason for telling you that. But that kind of brings the wet bulb temperature into the picture as well. It's quite an easy thing to calculate because you've got the lines there to do it. Okay. So let's look at an example. So here we have an early morning tephigram over land. There's no cloud in this example, hypothetical example. And we start off, what have we got? We have an inversion. So this is the temperature, and the temperature, it basically has this little nose in it. This we would call a radiation inversion. It's radiation referring to the emission of infrared radiation from the land surface overnight. So this is early morning, over land, no cloud. Land cools, obviously, and we get that transmits itself to the lower levels of the atmosphere, and we get this inversion. As we go through the autumn, these things become more and more important, the light, because the night gets longer, and if we're very unlucky, we get fog by this method, because it just, basically the land just cools and cools and cools and cools, and you end up with fog. Nasty, unpleasant stuff, particularly in November. Then as we go up, we get into the boundary layer, and this is the top of the boundary layer inversion, and this region here is the free troposphere, and we reach the tropopause up here. So, and again, on the dotted line here is the dew point. Okay, so is this profile stable to convection? All right, well, let's ask the question. First of all, if the temperature falls off with height more steeply than the dry adiabatic, then it's unstable. But in this case, it doesn't. You can see this is the dry adiabatic here. And so, in each case, temperature falls off with height, but a long way from there, and similarly here. So, at each point in the profile, it's stable to dry convection. So, it's a stable profile. It's not saturated anywhere, and so we don't have to think about whether it's unstable to saturated convection too. Okay. And if we lift a parcel of air on the surface, what happens to it? Well, basically, it obviously stable, it becomes colder than the surroundings, and it will sink. So here is a nice stable profile. The lifting condensation level is 930 millibars, but you're not going to see any cloud there. You're not going to see any lifting unless you force this air upwards by flow over a hill or something. Okay, so it's stable, but it doesn't stay that way. Because after the early morning, after the night comes the day, the sun shines on the surface of the earth and warms it up very quickly if there's no cloud. I showed you this picture before. This is the wind profile picture showing the growth of the turbulent boundary layer. These colours are basically a measure of the turbulent intensity. So you can see early morning you've got very shallow turbulent layer, and then the growth of the turbulent layer during the day. So basically that turbulence is due to convection. So the convection grows during the day as the energy of the sun drives the mixing of the atmosphere, drives convection. Now, how does it do that, and how do we see it on the tachograph? Well, in this idealized picture, I'm going to keep the dew point the same. I'm going to say all that's happening here is the sun's heating the surface. That's it. There's no evaporation of water vapor or anything else. These things would happen in reality, but in this case, not. So what happens is the surface of the Earth warms, and you can see these successive increases in the temperature. Now, when you start heating the surface of the Earth, suddenly the bottom little bit of the atmosphere becomes unstable. It becomes warmer than its surroundings if you lift it, and it keeps on lifting. And so you basically find that a parcel of air at the surface would lift until it reached this black line. And then as it keeps on heating, it will lift a bit higher, a bit higher, a bit higher, and a bit higher. So that's because it's got more buoyant energy because of the heating by the sun. And eventually, you get to the local lifting condensation level, which would be in the afternoon, and then you get some cloud. And once that happens, the parcel of air is actually now, so now it's saturated, and this portion of the black curve is sloping like that, and it's steeper than the saturated adiabatic. So now it is convectively unstable, and in fact it would rise up its own accord then to here, and it's met the environment again, and you've basically got some boundary layer cloud at the top of the boundary layer. This is a very typical picture that we see on clear days, where you start off in the morning with a beautifully sunny morning, and then by midday or something it clouds over and you think, oh, where's the sun gone? Well, this process is what's happened. Okay, so what I'm showing you there, so we're starting to look at not just the temperature, but at stability of the atmosphere. In other words, in this lower layer of the atmosphere, because it's heated from the bottom, it's unstable, the thermals can rise. This is dry convection. It's not necessarily, it's not condensing until it gets to this point here, and that's when you start getting the the condensing. And of course, actually, that's a better picture for what happens during the day. So, any questions on that? Yeah. So that's using the tephrogram. What's the tephrogram doing? It basically allows you to estimate where the ground base is going to be. It allows you to say, okay, I think it's going to warm up to 23 degrees today at the surface. Okay, well in that case then all I'm going to end up with is some fairly shallow cloud in the boundary layer. How do I know how much it's going to warm up? Oh, that's really, really hard. One of the things that these meteorological models do very badly actually is surface temperature. And one of the best ways of estimating surface temperature is to get a really experienced forecaster who knows the area that he's forecasting for, because it tends to depend particularly on details of the local topography. But still, that's an aside. That's showing you how to use the tephrogram to look at stability in that case then. Okay, so let's ask, well, let's suppose I've got something that will push this parcel upwards. I don't need to rely on the sun now. I'm saying, okay, well I'm taking this profile. This is it. This is its done. It's 23 degrees. It's produced this profile here. What happens if this profile flows over a hill or something and it's lifted further? Well, clearly, it'll get into this region, the parcel will get into this region where it's colder than its environment, so it'll want to sink. So in order to get it to go through here, you've got to provide it with energy. And that energy, because the tephrogram, remember the units are temperature and entropy, and therefore area on the tephrogram is energy. Integral of TdS will give you energy. So this area is called convective inhibition, and it's the energy you would need to give to a parcel of air to get it to over this little hump. And once it's reached this point, suddenly, okay, it's saturated, remember, and here's the environmental curve, here's the saturated adiabatic. The parcel now is buoyant, and it'll rise all the way up to the tropopause, and you have a lot of energy potentially that you can release, and this is called the convective available potential energy. If you don't have any CAPE, that's the acronym is CAPE, C-A-P-E. If you don't have any CAPE, you're not going to have any convection, any deep convection. Convection in the boundary layer, but not deep convection. On the other hand, you can have a lot of CAPE in a profile, but no deep convection if you have no means of getting past the inhibition. Okay, so if you have too much inhibition, you're not going to get deep convection. If you don't have any energy, you're definitely not going to get any deep convection. So there's a lot of people who study convection talk a lot about CAPE and SIN. And you're into this SIN, by the way, is what they call it, C-I-N, not S-I-N. And you have a rather counterintuitive result, actually, in meteorology. In order to get really, really big thunderstorms, turns out that you actually do need to have inhibition, because in order to get something really big, you've basically got to build up energy down here until it can break through the lid. If it gets through too early, you just get fairly shallow thunderstorms. That's energy. So deep convection develops when you've got small amounts of SIN and large amounts of CAPE. You need some SIN, otherwise there's no buildup of energy in the boundary layer, and you often need mechanical forcing to give you SIN. So, to overcome the SIN. Now we can go back and look at this profile here. So this is a profile in that region where there was deep convection. Okay, this is at the toe of Sicily where there was deep convection this morning. And what we can clearly see here, well, this profile is actually absolutely unstable in the bottom here. its lifting condensation level is going to be somewhere around here. These are the these are mixing ratio lines. And so all of this part of the profile, your cake is something like this. All of this part of the profile is convectively unstable. In other words, this part of the layer can lift simply through dry convection, and once it gets saturated here, it's going to give you a lot of deep convection. That's a very, very unstable profile. You don't often see those. And needless to say, you have got very large thunderstorms in that area at this time. Okay, so that's an example of a very unstable profile. This is an example of a not unstable profile, much more typical. This is Valencia. The air is saturated, all right, no problem with that. The two lines lie together, but very clearly it's stable in the bottom here, and it more or less follows the saturated adiabatic in this region where it's saturated. So it isn't unstable. So that's a stable profile, and you wouldn't expect to see deep convection here, or indeed any convection at all, and indeed you don't. That was in Valencia, and that's just an example. Okay, so back to this one. There's one last thing I want to just look at, which is, and this is a very common way of releasing deep convection. So we've talked about air flowing over a parcel being lifted. Now I'm going to talk about an entire layer of atmosphere being lifted, because that's in reality is what happens. If you think of air coming off the Atlantic and flowing over the Pennines, then the entire layer flows over the Pennines like that. And so the entire layer gets modified. And it's not just the temperature of the layer, but the stability of the layer as well. And here's an example then of lifting. So here's a profile, and as we can see, it's a nice stable profile. Nothing, there'd be no convection here, nowhere near dry adiabatic, and in fact, it's not near saturated adiabatic. It's not near being saturated either. Although this part of the profile here, it does lie to the left of the saturated adiabatic curve. It is conditionally unstable. Those definitions are on the handout, by the way, the definitions of these conditionally and so on names. So now I'm going to lift each of those dots by 50 millibars. Here's the first one, the one at the surface. Lifting by 50 millibars just means pushing it up in the vertical. What happens? Temperature falls down the dry adiabatic, dew point comes up the mixing ratio line, they don't meet, you've just got unsaturated air. Well, okay, it's a bit colder, that's it. Nothing to shout about. Now let's lift the yellow one. Whoa, this time they meet. So now we've got cloud, very familiar hill cloud. Now we try the blue one. The blue one's actually giving you, and I've done the blue one and the purple one. So you can see the blue one where the two lines are quite close together, they meet pretty quickly, and this is a little bit of a saturated curve. And that shows you that there's hill cloud in this region, and then as you take these points above, they don't meet, so the cloud is limited in scope. There's the hill cloud. And drawn as a grey line on there is the temperature profile of the slab of air once it reaches the top of the hill. So it does this. Now, is it stable or is it unstable? So this is the question. There are parts of this are now saturated. So this part here is saturated, but actually it's pretty much following this saturated adiabatic. Its gradient is not, definitely not strongly to the left of this one. And so it's kind of neutrally stable. You wouldn't expect to see any convection. You just get a claggy day if you were walking in the hills on this day. On the other hand, if we try doing it with this, which is a profile more like the one we saw from Sicily, you start to lift this, and So this grey curve is the lifted curve, and clearly we have now got large sections of this where it is connected to stable. This is the saturated adiabatic from the surface, for example, and it straight away the thing goes unstable. So you would expect to see on this day thunderstorms kicked off by flowing over the hills. Just a little bit of uplift would be enough on that day to give you thunderstorms over a small hill. Generally speaking, we don't see that too often here in the UK, but what we do see is thunderstorms kicked off by things like sea breezes, which are also things where you can get uplift of air. Sea breezes also cause uplift, and they very definitely can cause thunderstorms. And those of you coming from China will have seen a lot more of these near your coastlines, where you've got a lot more energy coming from off the warmer oceans. Okay, so that's potential instability. These different kinds of instabilities are defined. I'm not going to write them all down. They're defined on the sheet. Okay, so that's the end of today's lecture. Any questions or comments on that? It's not meant to be immediately obvious. You do have to do the examples in order to understand this stuff. Yeah? But if you have problems, please come and ask. Okay? Good. See you next week. Hello.
I've seen two types of epigrams. One type is keep entropy and temperature in a straight line.
Yeah, and the other one's a skew T, which doesn't.
Yes, skew T. For when we are calculating K, we are just calculating the area in the epigram.
Yeah,
so,
that's right.
How do we know that the two area in these two types of epigram are the same?
Well, then
or at least
yeah, the skew T is not a temperature entropy diagram, you know,
yeah.
And so the area on that is not quantitatively a measure of instability. Whereas to measure CAPE, in other words, you can't just measure the area on a skew T. You can on a tetragram. You could just take a piece of graph paper and measure little dots, little squares and things, and you get the area. You can't do that with a skew T because it's not that sort of diagram. But it's the one that's most commonly used. It's probably the one that the Chinese Met Office. Yeah. Certainly the one that the Americans use. So, and if you go to Wyoming, where we all do to get our plots from, so this is Wyoming. That's the one you're talking about, the skew T. Yeah. Yeah. It's just.
So the area installed here are not really the CAPE.
No, if you want the CAPE, you can read it from here. It tells you what it is on the right-hand side of the plot. It's not as... I've never really used these because I don't... You know, I know that they use them in other countries, but we've always used tetragrams in this country, and they're more straightforward to teach. It's a more obvious link, you know, with the basic theory. Whereas this is less of a clear link with the basic theory. I mean, they both work, and you can obviously work with either of them if you want to. Yeah?
Thank you.
Okay, that's fine.